Hey everyone, Statsland. Today is going to be our final look at Chapter 3, and we'll be looking at outliers and their effect on the least squares regression line. So you probably noticed that there hasn't been a whole lot of calculation of the least squares regression line, and that's kind of the way it is. We don't actually compute this by ourselves. There are definitely equations that you can use, and we've probably talked about them in class already. But for the most part, we just kind of let our calculating machines do the heavy lifting for us here. So if we haven't talked about it in class, make sure you ask me about calculating that least squares regression line. And yeah, let's get started with outliers and the least squares regression line, the final section here in Chapter 3. So it says to go to Staplet.com and find the link for correlation and regression. And let's go ahead and do that. A little hard to find here on Staplet. It's actually down at the bottom with applets for the practice of statistics. I'm going to go ahead and click that, open up a new tab, and we'll go to Statistical Applets, and we're looking for correlation and regression. This brings up my third window. And what are we supposed to do here? Well, we're going to click in the graphing area and add 10 points in the lower left corner so we can get a correlation about 0.4. So let's go ahead and get some points. Their correlation coefficient is 1, 0, 0.3. Notice I'm clicking these all in the lower corner. So I've made the correlation worse here. So I got to follow the pattern a little bit better. Follow the pattern a little bit better. And how many points do I have here? 1, 2, 3, 4, 5, 6, 7, 8. Got to get 2 more. 9. Oop, that wasn't very good. And 10. Okay, so let's adjust this a little bit. Okay. 4, 4. 4, 2. 4, 1. Still 4, 1. There we go. 4, 0, 4. So here we've got 10 points. We've got a least squares regression line. Next, we want to check the boxes to show the least squares regression line, and the box to show the mean and XY line. Okay, now we're supposed to sketch this into our StatsMedic paper. All right, like most of you, I'm just going to screenshot that over. And the next thing for us will be to, for each of the following situations, we're going to add the point to the scatter plot and decide if the slope, y-intercept, and correlation increase or decrease. So we're going to add a point to the far right side on the horizontal line for the mean of y. Well, which one is the mean of y? Over here, horizontally, we have y bar. Remembering that y is a vertical distance, so this says that the y coordinates are all the same at that y average line. The vertical line here, that's parallel with the y-axis. That's x bar. Again, anything over on that line has the same coordinate as the average of the x values. And of course, the blue line here is the least squares regression line. Okay, so now we can get to number 2. What's going to happen to the slope, the y-intercept, and the correlation if we add a point on the far right of the horizontal line? So right about here. What if we added a point right about here? What would happen to these values? Okay, so if I added a point here, we are no longer in pattern, so correlation would go down. That seems pretty clear. Adding a point there, the y-intercept, well, that's not going to. Is that going to move the line up or down if I put it there? And if that's the average y value, then I don't think that's going to change the y-average. So that line is the least squares regression line is going to kind of stay the same. The slope, however, that coordinate right there is going to have the effect of pulling the slope downwards like that. That's going to pull that line down along this fulcrum, and actually, so that's going to decrease the slope because the least squares regression line is going to be pulled down toward that point. And if this gets pulled down along this fulcrum, that should mean that the y-intercept is going to increase. So let's test our hypotheses. Let's go over to our applet, and let's add a point right over here at the very edge. Let's see what happens. All right, adding a point, boom. Oh my gosh, that decreased the slope dramatically. I'm going to undo it, and let's pretend that the left side of the screen over here, this left side, this is the y-axis. If that's the y-axis, notice how the y-axis increases. Or the, what am I saying? The y-intercept is going to increase in value. It's going to go up. And then let's pay attention to the value of the correlation coefficient. That correlation coefficient is going to decrease quite dramatically. It goes from 0.4 to 0.09. So that's all the evidence we need. We saw that the slope is going to decrease, the y-intercept is going to increase, and that correlation is going to decrease. Remember, a lot of this is a consequence of the fact that we were putting a point that was out of the pattern, not in the pattern of the rest of them. What happens if we added a point on the far left side of the graph on the horizontal line for y bar? Okay, so let's put that point hypothetically. Let's do it in green. What happens if we added a point here? Okay, well, just like before, we would probably expect the least squares regression line to get dragged toward that point. So that would also increase the y-intercept. That would also decrease the slope because this whole line would tilt downwards. And then the correlation would also decrease because, again, it's going to be not in pattern or not in line with the rest of the coordinates. Let's test out that hypothesis over here. Adding that new point here. Okay, so notice that the correlation decreased, but not as dramatically as before, because it's not as far out of pattern as putting the point on the far right side. Notice that the slope decreased, and when the slope decreased, that brought the y-intercept up. So it increased the y-intercept. Not a lot, just a little bit. So like the previous example, the slope is going to decrease, the y-intercept is going to increase, and the correlation is going to decrease. Okay, let's move on. What if we added a point below the least squares regression line on the vertical line for the mean of x? So what happens if we put a point right here at the very bottom? Okay, now that's again out of pattern, so we would expect correlation to decrease. And what we would see here is this whole line would be dragged downwards toward that point. Okay, it wouldn't tip the least squares regression line. It should just drag the entire thing down. So if we drag the entire thing down, that slope is going to stay about the same, but the y-intercept is going to decrease. So here we are at the simulation, at the staplet, and we're going to put a point right here, and what will happen? And it's actually kind of hard to see. Notice how the entire line was dragged down. So the slope stays about the same. Correlation is decreasing to 0.333. And the y-intercept is also decreasing. Okay, lastly, what happens if we added our vertical line onto the mean of x bar, the mean of x, the x bar line, but above that vertical line? So we could probably take a guess that if we added a point way up here, it's going to drag the least squares regression line toward it, but it doesn't have to tip it, it's just going to move it upwards. So that's going to increase the y-intercept, keep the slope the same, and again, the point is out of pattern, so correlation is going to decrease. So let's add that point and let's see what happens. Okay, so kind of like what we predicted, that whole line is just being dragged up. And the correlation is decreasing. The slope is staying about the same. And the y-intercept is increasing. So that brings us to the third question here. Which outliers had the greatest impact on the least squares regression line? Vertical outliers or horizontal outliers? So horizontal outliers have the greatest impact. They have more leverage because they're further away from the fulcrum. And what is the fulcrum? I'm glad you asked. The fulcrum is that coordinate x bar, y bar. Now, if we can summarize what happened here, for A and B, if we add something along horizontally, these had the effect of tilting that least squares regression line, tipping it up or down along the fulcrum or the balance point, which would be that coordinate x bar, y bar. While C and D, they have the effect of either lifting or pulling down the line. So this makes sense. And of course, whenever we have a point that is not along that x bar, y bar axis, then it's going to do a combination of these things, both lifting the line and tilting the line. And that brings us over to our outliers and the least squares regression line. So a good least squares regression line, which we should talk about, a good least squares regression line will have a low value of s, so a low standard deviation of the residuals, and it's going to have a high value of r squared. So it's going to have a high reduction in residuals, a high reduction in error. We said something earlier about the least squares regression line and the equation, and this is the least squares regression line equation. Y hat is equal to b naught plus b1 x. Now, how do we compute all of this stuff? The first thing we would compute is b1, the slope. And I know earlier we've just been calling that we've just been calling that b. b1 and b are kind of synonymous. So the slope is equal to the value of r multiplied by sy over sx. Now that is a lot of calculation to do. Calculating r, calculating sy, and calculating sx, any one of those by themselves is really quite a lengthy calculation. So we just let our calculator kind of do that for us. Of course, if we're given all three of those values, or if we're given the slope in two of those values, we should be able to solve for the missing value. Now the y-intercept, to get that, b0, which is the same thing as a, that's equal to y bar, the average of the y-coordinates, minus the slope multiplied by the average of the x-coordinates. Basically, all LSRL go through the coordinate x bar, y bar. It's a fact. Look it up. Every least squares regression line will go through that fulcrum point x bar, y bar. Now that we have that, we can talk about, of course, this is the exact same thing over here. This is the exact same thing that we were just looking at. What are the effects of the least squares regression line? Adding a point to the left or to the right of the fulcrum is going to tip the line. Adding a point up or down from the fulcrum is going to have the effect of raising or lowering the least squares regression line. And of course, combination of the two could be obtained by putting a coordinate basically anywhere else. Now those are pretty big concepts. Hopefully we understand how to get them, and we will actually practice, especially this learning target 1, the equation of the least squares regression line. So check your understanding. We have a scatter plot showing the payroll in millions of dollars and the number of wins for Major League Baseball teams in 2016. The point highlighted in red represents the Dodgers on the far right and the Cleveland Indians on the upper left. So describe what influence the LA Dodgers has on the least squares regression line. Okay, so right over there, those are my Los Angeles Dodgers. They are an outlier in the x direction. So they are far to the right, too far to the right. So that has the effect of tilting the line, the least squares regression line, toward it. And that looks like as though it's going to decrease the value of the slope. Since LA is on the far right of the graph, it decreases the value of the slope of the LSRL, and it increases the y-intercept. Now the Cleveland Indians, describe what influence the point representing the Cleveland Indians has on the standard deviation. And again, it's not in pattern with the rest of the points, so it's going to increase the value of the standard deviation of the residuals. It's making that typical distance much greater. And also, since it's not in pattern, it's going to decrease the value of R. So we write Cleveland is far from the LSRL vertically, which means it has a large residual, and the large residual is going to increase the value of S, since S is just the standard deviation of the residuals. Since Cleveland is not following the linear pattern, it's also going to decrease the value of R squared, since the coordinates, since R squared is a measure of how well the coordinates follow the pattern. And lastly, number 2, we collect data from a sample of 15 high school students to investigate the relationship between foot length and height. The mean and standard deviation for foot length, you can read that, 24.76 and 2.71, and the mean and standard deviation for height, y bar, is 171.43, and sy is 10.69. The correlation between foot length and height is 0.697. So let's find the equation of the least squares regression line. Let's remember our formulas. Starting with B. B is R multiplied by SY over Sx. We'll substitute those numbers, and that calculates to 2.75. Now let's remember our equation for a, and then we'll substitute those values again, and then calculate. Perfect. We have a value for a and b. We are now ready to create our least squares regression line. So we're predicting height from foot length. So our predicted height is 103.34 plus 2.75 multiplied by foot length. And folks, that's our chapter on least squares regression line, relating two quantitative variables together. Good luck on your test, and we'll see you next time here on Chapter 4 for AP Statistics. Bye now.